Okay. Now, starting with the Kalman filter. The presentation which you can find in the e-learning system, of course, is or that looks like something like that. As I told you, the Kalman filter or the Kalman filters, because we have many variations, it's a huge topic. And here in this course, I try to flesh out really a few things, but enough, let me say, to be applied, or at least to be applied in some cases. This means I will try to give you the most important fundamental uh, elements. We can see also here, I start from part B, skipping the part related to the observability. I will try to tell you a little bit. If I have time in the last lecture, I will recover or I will show you some slides from the part A. Let me nevertheless go directly to the Kalman filter, considering the essential part of the Kalman filter, even though sometimes uh, uh, compacting the lecture, of course, it seems to be really a little bit complicated to be understood or to, yeah, also from my side, it's difficult to tell you or to be able to transmit what I want. In any case, I will skip the calculations, or let me say, yeah, the mathematical aspects, in order to point it out, the application part, even though again, sometimes skipping the mathematical parts is difficult to understand. But I would like to try to introduce the Kalman filter is in a very intuitive form. This means at the end, we will discuss, as always, the software, of course, the program with which you can implement or you can solve some problems. Which kind of problems? Yeah, as I a little bit told you before, typically everything which we cannot measure, assuming that the system is observable. About the observability, I already told you, I will sketch something. Observability practically means even though I measure, even though we will see also a different meaning of the observability, even though I measure a partial number of the output, I can estimate states and some disturbance. Do you remember, as I told you before, the disturbance must be known. The disturbance must be known. Yeah. Or estimated. This is the meaning or the usefulness uh, of the of an observer. In this case, the Kalman filter is in a particular uh, form of an observer. We can see a linear discrete Kalman filter as a state observer. The linear Kalman filter is in a particular Kalman filter, uh, which is which works in this case as an observer or the state observer at the beginning. But of course, we can consider also Kalman filter which estimates also disturbance of parameters, everything related to elements who which plays a role inside the model and the sense inside the system, I would like to say. Also parameters could be, can be estimated. Discrete, as I told you, I don't remember if I told you, the Kalman filter which we are considering is a discrete Kalman filter. We have also continuous Kalman filter, even though it's not so very often applied, but we can also consider something like that. Again, I will proceed without going in depth into the theoretical aspects. Here we can find an impossible literature. It's in a summary, which is available uh, in at this address here. It's the famous summary. Of course, nevertheless, is a good summary for people or scientists who already know a little bit about carbon filter because again, it's not, it's extremely compact. When the Kalman filter can be applied, again, the system must be observable. About the observability, where we come back later. Basically, you can consider the concept of observability connected or related to the connections between the states. I will show you a little bit in the future what I intend practically. But I skipped here the presentation A, the part A, because of sake of brevity in this sense. Yeah, again, is an optimal estimator. This means the Kalman filter tries to minimize the error of the estimation. This means try to minimize, let me say, the variance. We will see a little bit more in detail the covariance. What I will clarify what I intend. Let me say the error in general. No? The error of estimation is the minimal in case of some hypothesis, of course. As I told you, we have a many variation, extremely many variations of Kalman filter. Okay, very important. You can see at the end here that not a precise or detailed knowledge of the system is necessary. As I told you, exactly now, under some conditions, an optimal value of the observer gain is calculated. This means we have an optimal estimation. We will see what is the minimal gain, and this is a fundamental element. Now we have the last sentence, which is not really very well possible to be interpreted because I didn't tell you about the Lumberger observer, but let me explain a little bit the last sentence. Lumberger observer is one of the first, probably the first observer in the sense here, state observer, which works, or at least the structural virtue works well if we have a very detailed knowledge of the system, parameters in the sense, the dynamics very well represented. And let me say in its structural form without noise. Which noise? Measurement noise in this case. Because basically we will see we can distinguish between measurement noise, the noise which came from instrumentations through the measurements, and noise which came, or that comes, from the unknown part of the system. Also, this is noise, if noise means a lack of knowledge. We distinguish, we will see here in the Kalman filter, between measurement noise and model noise, no? System noise. In the sense that everything which we don't know, something which is uncertain, we represent an uncertainty, can be classified as noise. Model noise, system noise, depends on the nomenclature, and measurement noise. Again, we have a linear and nonlinear case. We will start with the linear case because the nonlinear is in the case of extended Kalman filter. We have basically two possible streamings: extended Kalman filter, unscented Kalman filter. We will sketch out just the extended. Is an approximation. No? Both extended and unscented are approximation of the linear Kalman filter. And we will use this in the presence in nonlinear models. Look at this representation which you already know from MPC, the motor, the same example. Why the same example? Because we will see that we can, in the project for you, it's easy to reconsider again this example here for controlling and for observation and so on. Proper definition. I measure the current just the current, I want to estimate omega and current too. Even though I measure, the Kalman filter offers the possibility to have a better signal after filtering, because it's an optimal filtering. This means the results is better than the measurement. Of course, under some hypothesis, and in particular under the hypothesis of a linear system. But we will see also with the linearization, we have nevertheless good results. Let me consider that I measure the current and I want to estimate omega, as I told you. About the discretization, I don't need now to tell you more. Why that? Because as I told you also today, we are considering now the Forward-Euler standard because our focus is not the discretization, but the Kalman filter. Of course, if I consider backward-Euler, if I consider a different method, which I didn't tell you because the course is not organized or not oriented to the discretization or the discrete problems related to modeling, to observation, and so on, it's really extremely difficult to tell you the difference without supplementary lectures. But believe me, keep in mind that the Kalman filter looks like totally different, I would like to say. Different. Anyway, these positions at the end of the slide are known. If I plug in here in the equation 1 dot and 2 dot, believe me, we we obtain these two equations which represent the dynamics, or better to say, the discrete dynamic of the model. Basically, it's discrete representation. With this discrete representation, or based on this discrete representation, we will realize the Kalman filter, which is in a controlled system, or the algorithm of the system, based on the model, based on the model. I realize again the representation of the model in terms of matrices and vector. This is known. No, we already done many times. We already done many times. You remember, I told you that if TS is very small, we lose the controllability. In the context of MPC, extremely important to choose an appropriate TS. Here is quite similar. If TS is very small, we fell down. Is not observable system. How we can see intuitively from this equation? If TS is very small, we have here 1, more or less 1. Let me say TS 0 theoretically. It's not possible, but let me show you 0 in order to understand. This is it, this is 1, this is 0, this is 0, this is 1. We have a system which is non-interacting, is decoupled. This means if I measure the current, I cannot receive information about omega because this element here is 0. If I measure omega, I cannot receive information about current because this element is 0. Why that? Because this element brings the information of omega in the first equation, and this element is vice versa, bring the information of the current in the second equation. This means measuring omega, I, the current, thanks to this element, if it's not 0, we have information about omega. This is the, let me say, roughly speaking, the goal, let me say, the task of the Kalman filter. When the Kalman filter works as an observer. But of course, this is the task, the goal of any observer. Yeah, independent if it's Kalman filter or other kind of observer. We have seen in word Lundberger observer, but we have sliding mode observer, we have everything, believe me. Discretization. Also here, I don't need to spend much energy because, as I told you, we know that at least this discretization, which is Forward-Euler discretization, putting these positions in the model, we build the general model characterized by the matrix A, B, C, D. Do you remember? I think you remember this. I will obtain this expression of the discretized model in which we have identity matrix plus A multiplied S is our discrete representation of the linear system, which A without the AD, basically in the notation is identity matrix plus A multiplied S, in which A is the continuous matrix. C and D does not change because this equation is not a dynamical equation. Now, let me introduce the notation of the Kalman filter as typical notation. We can see that the state variables are characterized by x is k, which n dimension, typically n is the number of states. This means xk consists of, means x is represent the state, which consists of n variables, for instance. Two variables we have seen, current and velocity. What about the impulse u? The impulse u, at this moment, we considered, for sake of brevity, just one input. But of course, in the processes, systems can consist of many inputs. But of course, it's still complicated. It's already complicated with one input. System matrix A is the matrix n times n. We have seen also now, with two states, we have 2 times 2. The matrix B, and this is interesting because the dimension of the matrix B is n. This means it consists of n row on L column. L is the number of input. We can see a little bit from here. What about WK? WK is new in our notation because represent the system noise or the model noise you can call as you want, which has the same dimension of vector x. Why that? Because if I have a state, if something is unknown, I can associate to this state a signal or a variable. Let me say, better to more precise, a variable. This means, in general, we can consider n variable. We will see which characteristics should have, or must have, or should have, let me formulate this sense, W. And then the second part, we can see we have zeta z, which is measured state variable, sometimes y, with m dimension. That could be 1 measurement, 2 measurements, and so on. Then we have the map of the measurements. Until now, we called C, 1, 0, remember. But this is just a notation. Very often in the Kalman literature, we find this notation here, but you can use whatever you want, which is m row on n column. Because if you remember the output equation, y, you remember, equals c multiply x plus d multiply 0. Here, d we will not consider, but could be also considered. But let me consider just the matrix C instead of H, or the vice versa. But D in this lecture is not considered. This means the system is strictly proper. I don't know if you remember from control system. This means no connection between input and output, but could be also considered. H at M consists of M row, for instance, 1 row. If I measure in output just one variable, on n variable, because I have the state. I don't know, this is a little bit obscure. Look here. I called instead of H, C, H is in typical notation of Kalman. We can see that I measure just one variable, the current. I didn't consider the omega. This we have 1 row. Why 2 states, 2 row column? Because I have to select the state which I measure. This D is 0 in our Kalman, but could be also considered. Structure of the Kalman filter. The structure of the Kalman filter can be summarized at the beginning with this scheme here, in which inside a step, or within a sample time, we try to realize, let me say, 2 stages. The prediction step, I don't like much, but I copied this picture from a lecture. The lecture, they say, a sample time consists of 2 steps. One prediction and one correction, and prediction step and a correction one. In order to obtain an optimal approximation of the states in the context of Kalman filter. Could be added state and disturbances. Could be added disturbances, state disturbance and parameters, as long as the system is observable. We have some inputs. At this moment, it's quite abstract, the representation. Let me go ahead. Let me share this information a little bit full, but look, the question number one is basically the model, a discrete model, in which we can see until here, I mean, if you don't consider W of k-1, we know everything. This means this model here is the model which considers also the process noise or the system noise or the model noise as you want, which is a vector of variable, stochastic variable. Now we will see exactly what is written in the last part of the slide, which try to get information, yeah, about the everything which I don't know. The second equation characterizes the sensor. We can see exactly as before, we called, instead of H, we introduced the matrix C with one row, two columns, and then we associated now here the measurement noise and the vector W, V of K, which is a little bit something similar to WK for the characteristics, but this is associated to the output, to the sensor level, let me see, and W is associated to the system, or to the state of this. Now, characteristics of this W and V, we can see that at the point 3, this condition basically represent the process noise with a normal probability distribution for a digital Kalman filter. And in this sense, Q is not the variance, but the covariance, assuming that we have more than one state, of course, otherwise it's the variance. Again, the probability distribution of the variable W is normal distribution with mean value 0 and given covariance must be known. Now, the mean value should not necessarily to be 0, but let me remain on the standard form. 0 is the particular value, but of course I can consider something not exactly 0. This must be said. But let me go to this. Similar consideration can be done for the stochastic variable V. You can see exactly similar. But of course, these two noise at the end of noises, at the end of the slide, it is written that these two noise are assumed to be independent, each other, of course. White, I don't remember the characteristic of the white noise is the contra spectrum on all frequency, and with normal probability distribution. Normal means Gaussian. No? We have Kalman filter without this hypothesis, of course we have. But I am not expert in this. I worked a little bit, I applied, but our experience is in extended, what I present in this course, and unscented Kalman filter. I don't have time to tell you about that, but it's based somehow with an extended Kalman filter in this sense. It can be used in case the system is not linear. Let me remain on the linearity. Look at the slide. Uh, Heavy slide, but at this moment, just a few words. I would like to a little bit to reintroduce the concept of the variance and then the covariance matrix. Variance of the variable is clear. No? We have a Gaussian, we characterize the variation of this variable, and then of course we can consider the mean value of it, and we can consider the variation in sense of Gaussian around this mean value. This is the variance. Why am I speaking about covariance? We're speaking about covariance because if you have a covariance matrix, if we have more than one signal, of course, we have to consider the interaction, fix this idea without going depth. I mean, in this matrix here at the end, which is base of the matrix G, in which we can see that each variable is compared, let me say, is compared with its mean value, we can see here. In this matrix Q, we have in the diagonal the standard deviation square. This means the variance. And the anti-diagonal elements, which is a little bit difficult to be interpreted, but we can say that the statistical interaction, this means, for instance, sigma 1, 2 is the variation of the current, if you consider a system consisting of current and velocity, the variation of the current when omega variate. It's a little bit abstract, this sentence, but can be assumed to a little bit to have an idea about these diagonal elements, in which sigma square ij works in general is characterized by this expression here. I don't know if you remember, in case of one signal, this is collapses exactly into the variance of this signal here. Let me say. Look at this slide. Discrete color filter, linear case. Now we go in depth on this. We can define an a priori estimation error, which basically is characterized by E k minus, which is, let me say, the true xk minus its estimation. Why I put the true in this form here? Because is this true? Is the true? No. Is this true? Because we assumed here that the system is linear, typically it's not linear. We assume that W consists just in white and Gaussian probability distribution noise. Not necessarily that is true. In fact, we didn't look something true for true. We tried to find a system which works, and not necessarily true. Works means that we are satisfied with the results, even though probably the modeling, everything which I told you until now, the sample time, could be also chosen differently. Then we have an a posteriori error covariance estimation, which is more abstract this time, in which nevertheless we have the same xk, the true of Kalman, minus something which I will tell you a little bit later. Also, x hat minus, I will tell you a little bit later, but we can see it directly here, what x hat k minus is. X hat k is unclear. Anyway, coming back to ek minus, we can see that this difference is xk, which is this one, minus x hat minus k minus x hat minus, which is exactly our deterministic part of the model. Deterministic means without stochastic, no? I didn't consider this. We will see later this a posteriori error covariance, excuse me, error estimation. This reflects a little bit the scheme here, no? Prediction, correction, and so on. But let me go ahead a little bit more in the more abstract sense. If you try to do the calculation, I mean, I plug in here xk, which is here. I plug in x hat k minus which is here, basically the deterministic part. Again, xk is this one. I can do the calculations. I will sketch the calculation, and we will see that we will end up in the equation B, which states how it changes. Let me say the error, to be precise, the a priori error covariance matrix, because if you look here, we have the a priori estimate, better to say, error covariance, which is the expected value of this product between the error as a vector, the error, a priori error, minus the a priori, multiply the a priori, the same a priori error transposed, is basically is the sum of the square of the both a priori error, which the a priori error we already defined, which pk, which is here in the middle, is the a posteriori error, even though at this moment we didn't define correctly, we defined correctly, but we don't know what this is. Nevertheless, I can anticipate this is the a posteriori correction, because as I told you at the beginning with this scheme, we have an a priori correction, or estimation, better to say estimation, and then a posteriori correction. Let me go ahead slowly, even though we have just 50 minutes. How we can demonstrate the equation B? Again, the equation A is an equation of the Kalman filter, which belongs to the Kalman filter. This means the deterministic model is extremely important, the Kalman filter. The equation B introduces in the algorithm some stochastic elements, matrix Q, for instance. We will see matrix P without minus here inside, at the step before, Now, the calculation I would like to skip, but I will sketch a little bit the meaning, how I can demonstrate this. It's easy. It's boring, but it's easy. I calculate the expected value exactly of this product here, in which once I plugged in xk, which I know, because it's this one, x hat k minus, I know, because it's this one. Believe me, extremely boring, all these calculations. You can do a little bit, you can scroll down alone also at home, but it's not difficult. The calculation is not difficult. It's just boring, absolutely boring. But you can see proceeding with some calculation, I would like to say algebraic calculation, we end up on this central equation, which we can see exactly in an abstract form, is a of k minus 1, which multiply a of k minus 1 transposed, which is exactly p of k minus 1. The a posteriori covariance matrix, which at this moment is, let me say, defined just here. But formally, we obtain this result. If you have time and look at the demonstration, it's not requires it for the examination. And then I will start to consider the expected value here, everything. Excuse me, A is a constant, AT is a constant. Yeah, the expected value represent this equation here, this part here, in which, or better to say, this expected value is represented here, which basically says how possible to express. Yeah, A is constant. This means come out from the expectation. The expectation of something which is constant remain itself. And then the expectation of AK minus 1 multiply AK minus 1 transposed, we formally defined here, which is we called a posteriori. estimate error covariance, a posteriori estimate error covariance. And I will use the linearity property of expectation, and we can distribute the expectation, let's say here, at least here, everywhere, but of course here, expectation of this product here, uh, it's no, because it's the Q, we can see here, because exactly what I told you at the beginning. Yeah, I told you, anyway, is the variance, or covariance in the sense, as here. And of course, this is a trivial consideration because uh, the hypothesis, or at least the hypothesis which I am considering at the beginning is the expectation or the minimum value equals zero, with mean value zero, normal with mean value zero. Anyway, we have also to apply some other hypothesis for this or property, for instance, this one, to end up, believe me, in this equation here. 1 second to I think here we cannot, this expression here came from the distributivity of the expectation. Basically, it's an integral, no, if you think in continuous. Let me see if I forget to say something. Mm. Let me go ahead with the equation C, which states the correction. If I put this equation as a possible hypothesis, in which I say the corrective variable xk hat equals xk hat minus previous estimation, plus a correction, which is stated in this hypothesis kk, which multiply the difference between what I measure and what I observe. What I measure, first variable, and what I observe, first variable, but observe. The name is measurement noise or residual, measurement innovation or residual, very important. And please remember that kk is something which can change. In our case, can change. This is the key point of the Kalman filter. The Kalman filter tries to calculate, as I told you at the beginning, an optimal k, which we call kk because it could change over time at each step, to adapt the estimation with respect to the dynamics or with respect to the signal disturbance which can occur. Here is the characteristic which I am, let me say, repeating the definition of the a posteriori covariance matrix, and of course the expectation of the true variable in accordance with what the true is for Kalman is exactly the estimation. The sentence here is due to the linearity. It's sufficient to point out, to observe that the Kalman filter maintain the first two moments of this distribution. Basically, also after the Kalman filter, these two properties will maintain. That we know already. Let me skip everything because I would like today, I would like to conclude If you want, you can try to do at home. But let me, in these 5 minutes, to introduce the last two equations, the basic equations. Let me consider here the trace of the a posteriori estimate covariance matrix, this PK, which at this moment is there, but I didn't tell you much. This is the definition which I already did. I already well, presented. If I now consider the problem to optimize this trace means the sum of the diagonal elements, the sum of the variance. To remember, the diagonal we have the variance of the states. If I consider to minimize the variance, it's nevertheless interesting possible solution because the variance represents the errors. This is, I copy everything, I copy again for you everything. Yeah, we don't need. Let me see what I would like to tell you. This is the equation C, which is presented, but the equation D and E will come directly calculating analytically the derivative of the trace of pk with respect to kk. You know from high school that to find the minimum for a quadratic function, because the trace of pk is in a quadratic function, standard deviation of the current plus standard deviation of omega and plus some different standard deviation if I want to estimate something. This is the K, which K, next week I will bring a book to show you how this equation appeared. This is the KK. Please pay attention to this. Let me conclude, and then I give you the task to look at these 5 equations and to understand a little bit the meaning, but we will come back here together in order to go in depth. Okay, this is one. And what is about E? This is easy. This value here, or that with this K here, we calculate pk through the definitions, through the equations which I introduced now, and we obtain this. These 5 equations, once applied, solve the estimation of state, and eventually we will see if I augment the variable of parameters of disturbance of a linear system, which can be modeled using wide Gaussian noise at this moment with mean value 0. A crucial role is played by matrix Q and R because we can see that in particular KK depends on both. Depends on R, depends on Q, and Q is our MP minus. This means Silvano is the guy which worked with me in the Kalman filter, says to me how I can tune. Yeah, the Kalman filter is not tunable. We can try to approximate the true Q and R, or we can try, I don't want to speak about the true because it's not correct to speak about the true, and a valid Q and R, which somehow optimize or estimate, better to say, the value which we want to estimate with the minimal variance, not the covariance. Of course, everything works if the system which we want to analyze is linear, and with the hypothesis on W and V, the noise. But we can see, nevertheless, some consideration on Q and R here in this text. Why that? Because if you consider Q very large, you have a large variation in the process noise. This means we don't trust the model. Indirectly, we trust the measurements. We can see from here that Q has an influence on the numerator Of course, we haven't something a saturation for large Q, but nevertheless, we try to for increasing Q from for small value, we try to increase K, increasing K, we try to trust the measurement instead of the model. This is the contribution of the model. This is the contribution of the measurements, which includes KK, which include the statistic meaning or the statistic inside of the Kalman filter. This means statistically, I will trust more the measurements, the contribution on the estimation, a posteriori estimation, the final estimation, is weighted by a relatively large K. Depends of the step, of course, on the step, of course. The same consideration can be done for R. If R is very large, we don't trust the measurements because we have a variation on the measurements, because the variance or the covariance is large. If this is large, we can see that K reduces. If K reduces, we trust more in the final estimation, the a posteriori estimation, the model. Now we can see that K is in weights, in adaptive weights of what? Of this difference. In literature, we call this difference, is written here, innovations. Try to do at home the consideration if Q is small and R is small, no? But easy to see because if Q is small, K is very small, theoretically zero if we trust totally the model. If we say the model is perfect, the model does not need an improvement through the measurements, this is zero or very small, and we obtain the a posteriori estimation using directly or just the a priori estimation. The same can be done, the similar consideration can be done if, as I told you before, if R is large. If R is large, we trust again the model. If R is large, we trust again the model because this large R reduces KK. I don't know if I made mistakes in but now it's correct. KK is small. If R is large, this means the measurements is not trustable. This means xk hat equal xk hat minus. We go ahead just with the model. Try to do at home what happens if R is small. No? I think I didn't mix. If R is small, this means we trust the measurements because R characterizes the noise of the measurement. This means no noise. Let me say R very small. If R is small, in the sense we try to increase. We try to increase KK, of course, for a given Q. For a given Q. This means if the measurements is trustable, we can see the contribution of the measurement here inside. Of course, here is nevertheless present. Is nevertheless present. The model is always present because when the model is not present, the model of this xk hat minus, which represent the deterministic part of the model, in case Q is zero and then we will go ahead the next time, P0 is null, is zero. What is P0? P0 is the initial value of the a posteriori error covariance. Or let me say the variance of the error which I have at the beginning. To start, look at this scheme here. To start the Kalman, I need the initial value of the states, but also the initial value of the error. The a posteriori error is characterized by the matrix P without minus. Even though I can trust totally the model, if P0 at the beginning, P0 means to start with the initial error, is not zero, the Kalman will consider KK not zero. And the reason is mathematically or computationally, we can see directly from here because P minus Pk minus, no, is here. Even though Q is 0, but if P0 is not 0, we will start to increase the contribution of K. Increase it, then of course, additively we will change, but it's not Kk 0, just if Q is 0, because the contribution to K is given also from or by the initial value of the error. Makes sense. Because the idea is to estimate the state, but the state does not depend just on the model, it depends also on the initial value of the error. Of course, if I totally far away from my, let me say, state to be estimated, I have to converge this. This means Kk cannot be 0. Anyway, this is a really intuitive idea or explanation of the 5 basic equations in the slide. You can find a little bit the demonstrations. You don't need to go in depth to the demonstrations, but if you want to go in depth, the equations are there. Next week, I'm not here. We will see in 2 weeks. We will simulate and we will repeat everything in linear. And then we will start with a nonlinear case in the form of extended Kalman filter. I don't have time to tell you about the unscented Kalman filter, which is a variation of extended, but with the same hypothesis. I mean, we are moving in the same frame. Same frame means, again, extended, unscented at the nonlinear form. We will see next week, after next week's simulations, and then the nonlinear case. The same frame means, as I told you, white, Gaussian, and mean value 0 of the noise. Independent noise, of course. W and V, at each step, they are independent. Okay, I have to conclude. If a question, I am here. Otherwise, yeah, we can see in 2 weeks. We have 2 lectures more in accordance with the in the calendar. It could be that the last lecture will go. I will continue to recover the lecture of next week, but we are on track in general. We are on track. See you after next week. It could be that it could be. I will send you in any case an information that I will not hear. The material is in an e-learning system. Everything I didn't upload the simulation because I did in Kalman filter because I didn't tell you.